Alright, so today we're going to talk about transfer of heat. According to the law of conservation of energy, energy or heat cannot be created or destroyed. So if you put hot metal into cold water, what's going to happen to the heat? Well, if it can't be destroyed, it's got to move from one thing to the other. Well, heat, right, will move from hot to cold. Right, so if it moves from hot to cold, that means our hot metal is going to transfer heat into our cold water. Okay, so what's going to gain heat? Well, our cold water. What's going to lose heat? Our metal. How much heat does the water gain? Well, if we have to conserve energy, the water has to gain as much as the metal loses. Right, and so the final temperature of the water compared to the metal. Well, when we put that piece of metal into the cold water, right, we are going to have this transfer of heat back and forth until they come to some sort of equilibrium. And so this point of equilibrium is where the temperature stops changing. So when the temperature stops changing, that's when their temperatures are equal. Okay? So we can use this information or this concept to determine what the specific heat of a substance is. Okay? So yesterday we learned how to use Q equals mc delta T. So let's just review that. So Q equal to mc delta T. If 12.5 grams of water is heated from 30 to 50 degrees, how much energy will be required to do that? So again, we're looking for the energy. That's Q. We know the mass, right? And we know our delta T. So when we always know our specific heat for water. So Q will be equal to M times C for water times delta T, in this case is 20. Right? And so Q is equal to 1046. Now here we have three significant figures. Here we have one significant figure. So if we round this to just one significant figure, right, that would just be 1000 joules. Okay. We've also talked about how to calculate heat of a phase change. And heat of a phase change, we take 25-gram piece of ice, right, this undergoes fusion to liquid water, right, which is just in the way it says that it melts to water. How much heat energy would this take? If you recall, we learned that Q equals mH fusion, right? And so we take our mass times our heat of fusion of water, which we find on our reference table, right, which was 334 joules per gram. And we multiply those together, and we get 8350 joules. The only measurement we took was mass, so that had two significant figures, so we need to round this to 2. 3 is our second significant figure, and we can round it up, so it becomes 8400 joules. So that's a review of the types of problems we've done so far. Let's see what this transfer of heat looks like. So, we have a piece of metal. It has a mass of 14.68 grams. It decreases its temperature from 109 to 30 when 25 grams of water at 25 degrees Celsius is added. What is the specific heat? And then we want to identify our metal using our reference tables. So what we've learned is that the heat has to be transferred from the water to the metal. From the water to the metal. So if we have, they have to be equal, right? And so our metal, right, went down in temperature, right? So its heat is being lost, right? So that's saying that this is exothermic, right? It's losing heat. Although it's not really losing it, it's really just transferring it to the water. So it's equal, but they're opposite in sign. Because remember, if energy is released, then it's negative. And so since the metal is releasing energy to the water, it's going to be negative. We also know that Q is equal to mc delta T. So we have a lot of numbers here. So let's make us a chart. And let's organize our information. Right? So let's call this side water and this side the metal. And then we have M, C, and delta T, right? So what's the mass of our water? Well, it was 25 grams. The mass of our metal was 14.68 grams. Specific heat of water, we look up in our reference tables, 4.184 joules per gram degree Celsius. We don't know the specific heat for the metal, that's what we're looking for, so we'll call that X. And then delta T is final minus initial. So our water starts out at 25, but it goes up to 30, right? So our delta T here is 5. And then our metal went from 109 down to 30, and so that's a change of 79. Again, the final temperatures are the same. Okay? Don't forget your final temperatures are the same. So we have the MC delta T information for water, so we can find Q for the water. So let's do that. That's 25 times 4.184 times 5, and that gives us 523 joules. And we're not going to round yet because this is just the middle of our problem. Okay, so the water is gaining this much, right? So the water is gaining this energy from where? Right, so from the metal, right? So if the water gained that from the metal, then the metal had to release it, right? So Q for the metal is equal to Q of the water, only they're opposite in sign. So that means Q for the metal will be negative 523. And that would have to be equal to the mass of the metal, which is 14.68, times specific heat of the metal, which we don't know, times the change in temperature of the metal, which was negative 79, because it decreased its temperature. And so then we solve for X. Of course, our negatives will cancel out. And we get that X is 0.45 joules per gram degree Celsius. Okay. And so then we want to look on our reference tables. If we take out our reference tables, it's kind of hard to see because the light is shiny. Turn that off. There. Alright, so we look at our reference tables and we can find the one that has specific heat of 0.45. So we see this column here that says specific heat, and we find the one that says 0.45. We have one here, 0.449. 0.449 is iron. That is close enough, right? So our substance is iron. Okay? So let's use pause and try this problem next on your own, and then play again, and we'll go through it together. Alright, so Q for the water is equal to Q for the metal, and we know that Q is equal to MC delta T. Alright, let's organize all of our data. We have our water and our metal. We have our MC delta T. So our mass of our water was 15 grams. The specific heat of our water, we always know that, 4.184 joules per gram degree Celsius. And then delta T, our water starts at 40 and ends at 50. So that's a positive 10 change. Next, our mass of our metal is 16.88. We don't know our specific heat. And our delta T, again, final minus initial, 50 minus 146 will give us a negative 96. Right? so we have our MC delta T information for our water, so we can find Q for our water, which is 15 times 4.184 times 10. And we find that Q for the water is 627.6 joules. Alright, and the relationship between the water Q and the Q for the M is that they are equal, but the M is negative, so it'll be negative 627.6 is equal to the mass of our metal, which is 16.88, times the specific heat, which is X, times the change in temperature, which was negative 96. Again, our negatives cancel out when we divide. And we find that our specific heat is 0.387 joules per gram degree Celsius. Right, except that I only get two significant figures, so that would be 0.39 joules per gram degree Celsius. We look on our reference tables on this specific heat chart, and we find the one that's close to 0.39, and we get zinc. It's 0.388, right, and so that's zinc. Right, and that concludes today's video.